Hi, welcome to another video in database internal series. Today we'll be discussing about B-tree basics, the B-tree hierarchy, and what are separator keys. And in the next video of this series, we'll discuss about the B-tree lookup complexity and then node splits and merges, which both of these are considered under the rebalancing operations for a B-tree. So without any delay, let's get started. So compared to binary search trees, B trees have a higher fan out and smaller height. We have already talked about this in a lot of our previous videos. B trees are sorted. The keys inside B tree nodes are stored in order, which means of course it is sorted. Now because they are sorted, we can use algorithms like binary search. So an example of this is, let's say you have 4 billion items and you want to search amongst those 4 billion items, it will only take 32 comparisons, right? This is, of course, we are leveraging binary search, and it has of course the logarithmic complexity. Now using B trees we can execute both point and range queries. So what are point queries? When you specifically have specified that okay, we want to see and check the equality amongst whatever keys you want to search, that means you're pointing to a certain specific key, so that's why it's called point queries. And range queries of course are expressed by these operators: less than, greater than, less than equal to, and greater than equal to, right? Okay, moving on to B tree hierarchies. So this essentially will give you how a B tree structure looks like, what are the components of it, and so on and so forth, right? So let's start. So B tree consists of multiple nodes. Each node consists of n keys and n plus one pointers. Why it is like that, we'll again come to this in later. Why n keys and why not n plus one keys? Nodes are logically grouped into three groups. We have root nodes, leaf nodes, and internal nodes. It's just like any other tree, right? Even if you're talking about binary search tree, you'll have all of these present there as well. But I just thought of including this just to, kind of brief you about the structure as well. Okay, so root node has no parents and it is at the top of the tree. Leaf nodes are the bottom layer of nodes that have no child nodes, and everything in the middle of it, which connects the leaf node and root nodes, consists of internal nodes. So these are all the other nodes connecting the root with leaves. Okay, so this exactly is how a B tree structure looks like. You have your keys stored here. For example, let's say K1, K2, and K3. And in this aspect, in this block, you'll have your pointers. So pointers point to different subtrees. And then of course you have your leaf nodes, which they don't have any childs. So they only contain the key values, right? So this is the root node. These are all the internal nodes and these are all the leaf nodes, right? So this is how a typical B tree hierarchy looks like, right? Very basic stuff. You store your keys and your pointers in a node, right? And you have here n keys and n plus 1 pointers, right? You have 3 keys and 4 pointers, right? Why it is like that, we'll come to that again in the next section of this video. So now, since B trees are a page organization technique, they're used to organize and navigate fixed size pages. So typically a disk block is 4 KB in size, and one B tree node is also 4 KB in size. So that is why it is called as a page organization technique. So they're used to organize and navigate fixed size pages. We often use page and node interchangeably, and that is the reason we use them interchangeably, because a disk node is what, a disk block is what, 4 KB in size, and of course the B tree node is also going to be typically 4 KB in size. Now this is of course not going to be consistent across different databases, but generally this is what is the node disk size and node size, right? Okay, now the relation between node capacity and number of keys it actually holds is called occupancy. How many number of nodes do you have, and how many of those nodes actually have data or have keys? That is what is called as occupancy. And splits and merges are considered as tree rebalancing operations or tree balancing operations. They're triggered when nodes are full or nearly empty. So I mentioned in the beginning of the video, in the next video, we'll discuss on specifically on node splits and node merges and how balancing happens. Cool. Moving on to separator keys. So keys stored in B tree nodes, they're called separator keys. Why so? So these keys split the tree into subtrees holding corresponding key ranges. What this means is that it'll get clear it will get clear very soon. So consider this as your typical B tree node. It has 3 keys, 1 key, 2 key, and 3 key, and it has 4 pointers, right? 1, 2, 3, and 4. Now, what each pointer points to is very important here. And now, before proceeding, consider that KS is a key that belongs to subtree. So, for example, this is subtree 1, this is subtree 2, this is subtree 3, and this is subtree 4. Now, KS belongs to these subtrees. So, when let's say pointer P1 is there, P2, P3, and P4. Now, what does P1 point to? So, P1 will point to some subtree which has keys which are lesser than K1. This is K1, and P1 points to a subtree which has all the keys which are strictly less than K1, right? What happens to P2? P2 points to a subtree which has keys which are greater than equal to K1 and strictly less than K2. So on and so forth. And the last pointer in a B tree node points to a subtree which has all the keys in that subtree greater than or equal to K3. So this is why these are called separator keys, right? These keys, they split the tree into subtrees holding corresponding key ranges. That is what I meant by that. Now, I hope this is it's pretty basic, and I hope it is clear. And this is how separator keys split a tree into subtree, right? Now, the first pointer in the node, it points to subtree holding items less than the first key. This is what we saw, right? KS belongs to subtree and it is less than K1, right? And the last pointer points to a subtree holding items greater than or equal to the last item. This is what we saw, right? KS here is greater than or equal to K3. And if you think about it, right, this is essentially leveraging the sorted nature of B trees. Because keys are stored in order, you see that, okay, this is a typical sorted fashion, right? KS is less than K1 in this block. In this block, KS is greater than or equal to K1 but less than K2. In this block, KS is greater than or equal to K2 but less than K3. And in this block, KS is greater than or equal to K3. So this is typical sorting, right? This is in order, right? So keys are in order. So now points to note here. So rather than being built from top to bottom as binary search trees, B trees are constructed the other way. They are constructed from bottom to top. And the number of so what happens because of that? Your number of leaf nodes grow, which increases the number of internal nodes and the tree height. So this is how typically a B tree is populated, right? Now, since B trees reserve extra space inside nodes for future updations and insert, tree storage utilization can get as low as 50%, but it usually is considerably higher than this, but it can go as low as 50%. Now, higher occupancy does not affect B tree performance negatively, right? Awesome. So I think for this video, I wanted to cover the basics and probably the lookup algorithm and the node splits and node merges I'll cover in the next video of the database internal series. I hope this was like a pretty basic primer, and I hope pretty much everything is clear. Separator keys essentially separate the keys into subtrees, and in the basics we covered how the hierarchy looks like root node, internal nodes, and leaf nodes. And we also typically covered how the search algorithm is logarithmic and with an example of 4 billion items and so on and so forth. And it has a higher fan out and smaller height, right? So I hope this was like a primer to your understanding of B trees. And I hope you understand now the hierarchy as well as what separator keys do and why they are important in ensuring that you leverage the sorting capability of a B tree, and in logarithmic time you do a lookup. Cool, awesome. Thank you so much for this one. I'll see you in the next one where we'll discuss node splits, node merges, and the lookup complexity and algorithm in B trees.